Okay, so this is the halogenation of benzene versus phenols. And what I'm going to talk about is how we halogenate benzene and why we need a halogen carrier to do it. And I'm going to compare that to phenol, which doesn't need a halogen carrier. And we're going to talk about why that is. So first of all, let's talk about benzene. Benzene ring is 6 carbons. Each carbon has a hydrogen attached. And we have got a p orbital in each of our carbons, and what these p orbitals do is they all overlap with each other. This one off. So all the top lobes of your p orbitals will all overlap, and all the bottom lobes from these p orbitals will overlap. And if you want to be specific, we'd say it's side-on overlap, because they're overlapping from the side, not head-on. So when they overlap, what we end up with is this ring structure above the plane of the carbons and another ring structure below the plane of the carbons. And we call this a delocalized electron ring. And basically my electrons just go around this ring. That's what they do. What this means is rather than my electrons being stuck in one place, which will have a high electron density, the electrons spread out around the ring. And what this does is it reduces the electron density. Okay, so benzene actually has a low electron density. Now, when it's reacting with bromine, what it needs to do is induce a dipole in my bromine molecule. So as the bromine approaches, the electrons in the ring push the electrons in this bond down. So rather than being in the middle, the electrons are closer to this bromine. Now the charge of an electron is minus, so this bromine gets a negative dipole and this bromine gets a positive dipole. And then, because that's positive, my ring can attack it and react with it. However, remember we said earlier that all of the electrons in this ring are spread out around the ring rather than one place. That means that there's not much electron density. So the dipole they induce is very, very small, almost non-existent. And in fact, it's so small that it means the ring can't attack it. So normally, benzene does not react with bromine because the electron density is so low, because it's spread out around the delocalized ring, that it can't induce a big enough dipole. Okay? So what we need is something that can, in a way, make the dipole for us. And what we use is a substance called a halogen carrier. Now there's lots of different halogen carriers you can use. You can use, if I'm using bromine, Al-Br3 or Fe-Br3, or rather than bromine, I could have chlorine there instead. So there's quite a few you can use. In the exam, you can state any one you want, and that one's an easy one to remember, Fe-Br3. So that's the one I'll use in my example. Now Fe-Br3 reacts with my bromine, and essentially it rips off a Br-. So if it's ripped off a Br- and attached it to itself, that'll be Fe-Br4-, and that's going to leave me with Br+. So it's created this electrophile, and this Br+ can then be attacked by my benzene ring because it has this positive charge. The reason Br2 can't be attacked without my halogen carrier is because it doesn't have a big enough positive charge to be attacked. And here's how it works. You have your benzene ring and you have your electrophile which you've generated. A pair of electrons from the ring are given to the bromine to form a bond. And we show that with a curly arrow like that. From the ring to the Br+. Now remember, each of these carbons actually has a hydrogen on it. Now I didn't show this before, but they are there. So my bromine is now attached to the ring, and I'm going to draw my hydrogen on, which was there before. I've not added a hydrogen, I'm just showing it, whereas before I didn't. This ring has given some electrons away, so it's now been broken. So you draw like a little smiley face to show the broken ring, and it will have a positive charge. It's important we draw the positive charge near where the bromine has been added. So the ring isn't broken down here or over here, it's broken where you've added the bromine. And then what happens is the pair of electrons in my bond to the hydrogen is given back to the ring to make the ring whole again. Don't draw this curly arrow coming from the hydrogen, because all hydrogen is a proton. And we need to draw it from the electrons which are in this bond. So that will give us a final product of my hydrogen, which has lost its electron, H+. My ring has now been remade, and I've got my bromine attached. Okay? What then happens is, what I've just rubbed off, I had FeBr4-, and my H+ that we make in this step, they react to regenerate your halogen catalyst. Remember, a catalyst doesn't get used up. So it'll be FeBr3 and HBr. So you also get some hydrobromic acid. Okay, and that's how it works in benzene. Let's have a look at phenol. Okay, phenol is just a benzene ring with an OH attached, swapped for a hydrogen. So we're still going to have this delocalized ring structure with its low electron density. However, now we've got this oxygen attached. And oxygen has got lone pair of electrons in a p orbital. And just like we did here, this p orbital will overlap with these rings, extending the ring structure. It's a bit like a tennis racket. And when it does that, we have this extra lone pair of electrons added to my delocalized ring system. So more electrons, more negative charge, more electron density. So now, when my Br2 approaches, whereas before there wasn't enough electron density to induce a big enough dipole, now we've got these extra pair of electrons, making it more electronegative, so we do get a big enough dipole. And this can then be attacked by the benzene ring. And in fact, it's so good, rather than just reacting with one Br2, it reacts with 3. So my reaction is phenol plus 3 Br2, and then just like before, it's the same mechanism, so the bromine swaps to the hydrogen, we'll end up with and we've swapped a hydrogen for a bromine. We've got a bromine left over there, so we plus 3 HBr. Okay? And that's the differences between phenols and benzene and how they react with bromine. Notice that these bromines always go on carbon 2, 4 and 6, because that's carbon 1.